Good afternoon and welcome to the 12th problem solving session of the course Fundamentals of Semiconductor Devices NOC 24E02. This is April 13. This is the last session, but I'll also have a revision session tomorrow on MOSFETs. My name is Amit. I'm a PhD student at ISC Bangalore. Quick summary, we have been talking in the week 1 we talked classified materials based on their electrical conductivity into metals, insulators and semiconductors. We saw semiconductors are a unique material class in the sense that that happens actually when you bring a large amount of, let's say, 10 to the power 23 amount of silicon atoms for this discussion close together. What happens is that orbitals tend to overlap and they form bands, energy bands. So this is the lower energy band which is filled up to this energy level, we call it EV, and there is some another energy band above EC which can also be filled, but between these EC and EV is something which is not allowed. Hence this is also known as the energy gap or the forbidden gap, this gap, that is, right? Electrons can reside below below EV or above EC, right? And what we can also do is we can excite the electron from the valence band to the conduction band, and the electrons can also recombine with a hole in the valence band and release a photon, which you saw the basis for LED, right? And but please note that the electrons which are there in conduction band, they are not free to move. Please remember they are in a lattice which may have some ions, and it will definitely face some kind of potential which we call the periodic potential, and we modeled them using the Ronick-Penny model over here. And this is potential with respect to x position, with respect to position. And what we can also now draw is something called the band structure. This is the band diagram. Band diagram is between energy and real space. So x-axis here is space, position rather. And if we draw the energy versus wave vector k, which is 2 pi by lambda, we can now visualize these bands as something like this. So this is your conduction band, this is your valence band. Again, these are based on quantum mechanics, so there are discrete energy levels, but they're very close to each other, but they are these energy levels that are there. Okay, and what can happen is that these so we can quantify these energy levels in, let's say, talk about in EC, in density of states. It says that the number of energy states per unit energy per unit volume is density of states in a 3D system. This is directly proportional to square root of E. And having these energy states is one thing. Another thing is whether electrons are there or not. That is given by something called the Fermi function, where it's essentially a probability which is defined as exponential of E minus EF over KT. EF is some arbitrary energy level where the probability of finding an electron is half at 0 Kelvin, or for that matter at any temperature. If you increase the energy above EF, you can see that the probability reduces less than half. Okay, and what is the total concentration of, let's say, electrons? What you can do is simply integrate the density of states, that is how many energy states are there, times the probability they are occupying, times dE, because density of states, remember, is per unit energy, and you integrate from EC to infinity because electrons can only reside in the conduction band. When we did this and made some assumptions, we got a very nice expression, something like this. This is called the effective density of states. EF is energy, again, your Fermi level, right? And this is what we known as the carrier concentration at equilibrium. Okay, so right, but that's not the complete picture. Usually, for instance, in electrons, this number is around 10 to the power 10 per centimeter cube. If you want more number of electrons, let's say you want to conduct more current, what you can do, you can artificially dope this, and this is called the dopant, right? Except donors. So here this is called level ED. What can they do? They can donate the electrons at room temperature. Easily they can get excited to conduction band, and now there are electrons in conduction band, and which can then contribute to the current. The other flavor is what if we dope it with acceptors. Acceptor level will lie usually close to valence band. What can happen is that electrons at room temperature can now get excited and go reside in this at this level, and this frees up the holes which can now then contribute to the current. Okay, but please note that this excitation will not be there. There will be when they donate or accept electron, they come positively charged. So for instance, if you're doping with phosphorus in silicon, right? This is a n-type impurity, so the donated electron it become positive charged, right? This is the ionization process or this excitation process of electron. That might not happen because this still requires some energy. So below 100 Kelvin, it's what we see is incomplete ionization. However, if you increase the temperature even up, say, let's say up to 700, 800 Kelvins, what's going to happen is that you're going to use the extrinsic nature of the material and it will become inherently intrinsic. Then we saw the Ohm's law that J equal to sigma E. J is the current density, E is the applied electric field, and this was based on something called Vd equal to mu E, where Vd is the drift velocity. That is, you are subjecting an electron to some external electric field E, and what is the velocity that it will gain. So we saw that like something like this in the low field regime. Vd is directly proportional to electric field, applied electric field. This is what we got, and this it saturates at some time, because what happens is that this electron again is traveling in a lattice, so it will lose its extra energy that it gains at this to the crystal lattice, which usually comes out as phonons, or to put it more simply in terms of heat, let's say. Okay, and the another transport mechanism, this is one transport mechanism by drift, that is carriers are moving from one place to another. Other is diffusion, which happens due to concentration gradient, higher number of electrons on one side, low on the other. It's called diffusion, and diffusion constant d and the mobility are related by this Einstein relation, d by mu equal to kt by q. And the carrier density is denoted by drift and diffusion, but it can also have generation, like if you shine some light, or some recombination. If there are large number of electron and holes close by for a large amount of time, they can recombine, which saw in the case of single quantum well LEDs, the recombination. Right. Then we saw our first device, the p-n junctions, and so n, there are large number of electrons, they can now diffuse from right to left, and thus they leave behind positively charged donors, and these acceptors will accept the electrons, and you can see that it will set up an electric field which will oppose the migration of further electrons, diffusion of further electrons rather. Okay, so what happens is that ultimately this region is found where there are no mobile charge carriers. We call this region as a depletion region. There are no mobile charge carriers, and it's in equilibrium now, because electrons cannot travel. It's as if the system is frozen, right? And you can see there is an inherent built-in potential to this electric field here, and this is called the depletion width. And this is how typically the band diagram looks like in equilibrium. So in equilibrium, how do I know? This is p side, this is n side, this dotted line is EF, this is EV, and this is the conduction band. So this is the conduction band, this is the valence band. So if EC is closer to EF, we know it's n-type material, right? Similarly, this is the p-type because EF is closer to EV, correct? And so this is an equilibrium. So this is the depletion where the bands are bending. This is what we call the depletion region. And yeah, so what can happen is now you can apply this forward bias, which means applying a positive bias to the p terminal. So what can happen is that this barrier that you're seeing will get reduced, and the electrons which are over here, they can now diffuse to the other side and recombine over here, and they can complete the circuit now. And this is also known as law of junctions, Np equal to Ni square exponent of q Va over kt, where Va is the applied potential that you are applying over here. Okay, yeah, so this is about that. And 1 second. Okay, so and under reverse bias, you simply reverse the polarity of this. P is connected to the negative side, which we saw was the avalanche breakdown. So let's say this is your depletion region, an electron is here, right? And there's a large amount of electric field that is existing in the depletion region, because you see there is a slope here, right? So the large amount of electric field exists in this direction. Okay, this electron will now feel a force Q times E. Okay, it's negatively charged, so it will feel a force in positive x direction, and this electron, let's say its initial velocity is 0, right? So this is 0, but it's feeling a force, and thus the acceleration. What can happen, this electron, let's say by traveling this certain distance over here, it has gained sufficient energy now that it can knock out another electron from this atom. Similarly, they will again travel, and this electron again will travel, the original electron. They'll again encounter an atom, and they can again knock out another electron. So what you can see, this depletion region is wide enough, it can give rise to a chain reaction. This is known as the avalanche breakdown. Remember, ordinarily very less amount of current will flow, because if you recall, the expression is J is the current density, Js, and e to the power qVa over kt minus 1. This is what we have seen, and Js is usually nanoamps or picoamps, very small amount of current, but here a large amount of current flow after breakdown. Zener breakdown is something different in the sense that here we dope it so high that there's a band to band tunneling of electrons, so the electrons can now travel from this side to this side. This is p side, this is n side, and this can happen in highly doped semiconductors. But this also has importance in terms of voltage regulators. Okay, we saw many applications, we'll come to that later. And the Schottky diode is another type in the sense that, so we saw that you need to connect this wire to this p side. How do we do that, right? So we do that essentially by something called a Schottky, which is a metal semiconductor junction. So this is metal, this is a metal, and this is a semiconductor, right? And this we usually ground. Okay, so there are different kinds of contacts. So when you want to make such a contact, don't want it contributing like blocking the current in one side. That's called a non-rectifying contact, essentially an ohmic contact, and they work, Schottky diodes work on thermionic emission. Then we saw our second kind of device called the BJT, which we talk the NPN flavor. This is emitter, this is base, this is collector. We saw that doping, emitter should be doped high, base should be doped low, collector should be rather even lower, and we can bias it again. So there are different ways of biasing. So 2 into 2, 4 ways it can bias, and we saw the 4 regions: forward active, saturation, reverse active, and cutoff. We were most interested in this when emitter base is forward bias and base collector is reverse bias. Then the electrons will now diffuse from emitter to base. If the base is very thin, then very few amount of electrons will recombine here, because remember this is p type. The electrons can combine with the holes here, right? But if this is low, then if this is very thin, then the most of electrons will travel to the collector and the circuit will complete, right? And there is various other things that we saw. So emitter injection efficiency, base transport factor is essentially your IC over IB, and your current gain, which is current gain was IC over IB. And this is the base transport factor, that is how many number of electrons are reaching. This was actually IC over IEN, the number of electrons essentially coming from the emitter side per unit time. That's why the current IEN, right? And then we saw another version, another device, MOSFET. So this we have the metal, then we had the oxide, and finally the semiconductor. Usually we had grounded this. So what it does is that, so this is the metal, or we also call it gate. So let's say this is p-type semiconductor. If you apply a positive negative potential, you will attract these electrons at this interface, which is called the accumulation. If you apply some negative potential, you will repel the holes, essentially creating a depletion region. If you apply the potential even higher, so I'm going to draw now in a different way. So this is your Fermi level now, and this is your oxide. Okay, and so this is the Fermi level over here, right? And so what can happen is that in the bulk, this is EF, this is EV, this is still p-type, but you can say at this oxide semiconductor interface, this now material has become n-type because EF is closer to EC. This is known as the inversion, and the inherent terms which are involved, the bends have bent, essentially depletion is happening. What's happening is that the electrons are now coming to be collected at this interface. Okay, and now we can modulate these, then change the number of these electrons by applying, let's say, oscillating voltage over here, right? And we saw that we depict that through the CV characteristics, capacitance voltage. When you have negative bias, all the electrons holes will be collected over here, right? And you have something called the capacitance called the Cox, because this is the only capacitance that they see. However, in this other region, when this is positive, when the gate is positive, you can see a depletion capacitance also coming into role. So two capacitance series, the capacitance will decrease, and this will remain low if we have a high frequency, because you're changing the voltage so fast that the electrons do not have time to come from bulk to this interface. However, if the frequency is low, the electrons can now come over there, and the only capacitance you see again is the oxide capacitance. So this is how they look like. And there are some non-idealities. For instance, the work function of this metal and semiconductor may be different, and so we first try to achieve the flat band condition, and there may also be difference due to the trap charge in oxides. Based on this MOSFET, we studied the device of MOSFET. I'll cover this in more detail in the next session. So this is, you create two more contacts here. This is drain, this is source, these are N plus 2. So in the inversion, you have a layer over here of electrons, and if you can change, if you can apply a bias VDS, you can just contribute, you can clearly see a current beam there. Okay, and there are two, we saw the gradual channel approximation in the sense that, so the charge that is here is first due to the inversion layer over here, and also due to some depletion charge. Remember, there's a depletion region over here, right? This we saw in the gradual channel approximation, and ultimately if the drain bias is so high, then rather than having this triangular profile, rather than having this kind of a profile, this is source, this is drain, what can happen is that this is your oxide, by the way. So what can happen is something like this: source and drain, like this. The inversion charge is still there, right? But total charge at every this cross section has, the gate charge has to be equal to inversion charge, which is here, and depletion charge, which is here. Here you have depleted it so much the inversion charge is non-existent. Okay, so this is known as channel pinch off, and this is when the MOSFET enters into saturation. So you see this kind of a current, ID versus VDS. This is the saturation I am talking about, and over here you can see the on resistance. Transconductance is GM is nothing but delta IDS over delta VG. This is a very important expression. We'll come again to this way. Output conductance delta IDS over delta VDS. And body, this terminal, it's not useless, because now this can also be used to change the depletion charge over here, and thus it can have profound impact on the threshold voltage. Threshold voltage is nothing but when the strong inversion of the MOSFET structure starts. Finally, we saw the compound semiconductors, that is not just silicon or germanium, which are elemental. Something like gallium nitride, which is a 3,5 semiconductor, like CDTE 2,6, and 2D semiconductors like MOS2 and so on. Ternary means 3. This means alloy of aluminium nitride and gallium nitride, something like this. And we saw the Vagard's law, that how to estimate the lattice constant or band gap for this material. You can simply, this is like X times aluminium nitride plus 1 minus X times gallium nitride. This will give you for AL GA1 minus XN. So we saw this, and we also noted that it's not any material cannot be grown out of any material. They must be of the same family, that is compatible in terms of crystal structure, and the mismatch in lattice constant should be minimal, otherwise they'll crack due to the stress. Heterostructure is nothing but when two materials, when form of junction of semiconductor materials, have different band gaps. So something like this. These two materials have different band gaps. If you join them, we make a metallurgical junction, you have a heterostructure. So we saw that 3 types. This is type 1. The other type can be something like this, or this is the staggered type, and there is a third type which is more extreme of something like this. So here this is called a broken gap, and this is, I'm not drawing any, so this is known as delta EC, conduction by discontinuity, and I'm not drawing the built-in potential, but they will be there, right? Finally, for the last 2 weeks we were seeing the optoelectronic devices. First we saw light to electrical energy, which means typically your solar cell and photodetector. Solar cell works on photovoltaic principle, that is you shine some light and you'll get some current out of it. So if we see the IV characteristics of a PN junction, it looks something like this, right? If you shine some light, okay, if you shine some light on it, and by the way, so there's something called solar spectrum, that is, sun is composed of various wavelengths. Some of these wavelengths will be absorbed when the sunlight travels from the outer space to the Earth's surface. It will absorb in the atmosphere, and something we quantified that using the solar mass. It also depends, by the way, air mass depends on the time of, so for instance, when sun is overhead, we call it AM1, okay, and outer space is called AM0. Okay, and everything is measured with respect to AM1, yeah. So we saw also the efficient design of a solar cell in the sense that P layer has to be thin and highly doped, and this is your N layer. This was done to minimize the absorption in the P layer, because we want all the photons to be coming to the PN junction, and where they'll contribute, where they'll knock out essentially the electrons from the valence band and transport them to the conduction band, and then we saw this increase in current, right? So we can now observe that the current now looks something like this. This is the dark current, and this is what we know as the photocurrent, right? Current in presence of photons, photocurrent. This was known as the V short circuit, that is when the current is 0. How much voltage? V open circuit rather, sorry. And this is the I short circuit, and there is various terms like the fill factor and whatnot. We had talked about this. Solar cell is operating in 4th quadrant, photodetector is operating in 3rd quadrant. You can see orders of magnitude. This is let's say in picoamps. This current can be in milliamps, right? Just by shining of light, and thus you can detect a photon. Of course, that depends on the band gap and whatnot. And there's something called the external quantum efficiency, that is how many number of electrons are you getting for a given number of photons. The higher the efficiency, the better photodetector is. Finally, we saw in the last session, we saw LEDs, and we saw the different kind of radiative processes as proposed by Einstein, like absorption and emission. LEDs work on spontaneous emission, but and then that happens due to the recombination. So recombination essentially, as I told you, this is EC, this is EV. If the electrons falls from here to here, it can emit a photon. That's called radiative recombination. It can also happen that it does not do this. It can, as we saw, if there are some trap levels, right, associated here, so electron will fall here, and then maybe fall here, and then this energy is lost essentially as heat, as phonons, right. This is a band-to-band recombination. For an efficient LED, it must be a direct band gap material as well as radiative recombination. And we saw how the you can see we have seen this. So Eg equal to 1.24 over lambda. We have been seeing this expression where lambda is in micrometers. But you saw there is a slight deviation from that in the sense that, because remember, these are the quantum levels we are talking about. So actual wavelength emitted is slightly higher than that, right? And that depends on the effective mass. And this wavelength is not monochromatic. That is, you will not get exactly this wavelength, but rather a spread. And if you recall, we got something like this, right? So this is actually your intensity, or let's say, right, and this is your wavelength. Okay, rather it went something like this, not like this. So this is where it peaks. So this is just above Eg, right? Just above Eg, you see a peak over here, right? And there are various other terms which are internal quantum efficiency, which is how many number of photons you are generating for number of electrons that are entering into the active region. Other terms like external quantum efficiency and all, I'll not go into this much detail. And we also saw that how to quantify the light that is coming out of an LED, something called the luminous flux. This is, by the way, this is among one of these 7 fundamental basic SI units, right? Like time, distance, and all. One of them is the unit is candela. Luminous intensity is one of them. Okay. So today's session, if you went through the lecture, I believe you did, and there the professor is talking about something called the micro-fabrication, rather. And in that, before micro-fabrication, a few like transistors and in the sense and their applications, right? So among the transistors, we have already talked about, for instance, the drain current, right? We also talked about it when we talked about MOSFET, that the insulator is perfect, and we saw that the gate current is ideally 0, correct? Here we'll try to elaborate on that those assumptions are not entirely true. Ideally they should be, but we live in a real world. So how much are we deviating from those practices, from those those concepts, ideal concepts that we had talked about, right? And then the first of them is something called the breakdown characteristics. So that is, we already know in a PN junction, I already explained in the summary, like avalanche breakdown. So essentially, when the current is supposed to be very low, or ideally non-existent, 0 current, but let's say some very low amount of current, nanoamps, let's say. But all of a sudden, the current does not stay at nanoamps, it increases. That is effectively is what we call the breakdown. And that is usually happened, okay, 1 second. Yeah, that usually happens when the device is in off state. In the on state, it is supposed to conduct current. So on your screens, what you have is something called of the material of the gallium nitride. So this is a substrate. So we have grown gallium nitride on some substrate, right? And on top of gallium nitride, I have grown some aluminum gallium nitride. So this is essentially this was referred to as one of the lectures called MOSFET, or more popularly HEMT, high electron mobility transistor. Wired transistor, you can see the 3 terminals, the drain, source, and gate. Gate will control how much amount of, so where is the charge? In the MOSFET, we saw there is an inversion layer. It just so happens, due to some material properties of aluminum, gallium nitride, and gallium nitride, there is a readily available sheet of electrons over here, even at 0 gate voltage. Please remember, in the MOSFET or MOSCAP, we had to apply a positive gate potential in order to have a negative sheet of electrons. Here, even at 0 gate bias, this negative sheet of electrons is already present. So what you need to, hence you don't see any gate bias. So let's say we are talking about at Vg equal to 0. So the sheet of electrons is already there. This plus that you see is you can just assume is to balance the charge, because essentially they are electrically neutral, this structure, okay? And this drain, which is again N plus doped, as I told you in case of a MOSFET, right? So if you apply, let's say, some drain bias, and let's say I'm grounding the source and I'm applying some drain bias, let's say VD equal to 10 volts. So what you can see, the electrons are over here and now they can flow. This is high potential, so the electrons will start to flow from source to drain, okay, and the current will flow. You will have a flow of current now, correct? This is what is happening when the device is on. As I say, the multiple electrons are concentrated at this surface. This is the interface I'm talking about here. The electrons will already be there, okay, fine. So this is what I call the on state, okay. Now how do I turn it off? I want to see what is the breakdowns, and breakdown is study in the off state, okay. How do I turn this transistor off? Essentially I have to take out these electrons over here. So the electrons are over here between drain and gate, under the gate, and between gate and source, but I can control only the gate. So let's do that. If I apply a negative potential at the gate, it will repel these electrons. So let's do that. So we are applying some negative potential again, for the sake of continuity. I'll say Vs equal to 0, and again I am saying Vd equal to 10 volts, okay. And you are applying some negative potential at gate. Let's say Vg, I'm just giving some numbers, some around minus 5 volts. So when you apply minus 5 volts, what is happening is that you see the electrons have gone away from under the gate. They're still there between drain and gate and source and gate. So now even if you apply Vd equal to 10 volts and Vs is 0, electric field is there, but it cannot cross. There is no continuous path of electrons available, right? So this is when this here we are seeing, as I told you, the electrons are depleted below the gate, okay. So this is the off state. This is the off state. That is, even if you increase the, let's say, drain bias, you are not inside. There's very minimal amount of current is flowing. For the sake of discussion, let's say some nanoamps of current is flowing only. Here, the current that is flowing, the ID that you will measure will be in, let's say, milliamp. These are some typical numbers that we get. For instance, the devices that I make as part of my research work, these are some numbers that I'm giving you from that. So the drain current that I usually get is hundreds of milliamps, okay, at Vg equal to 0. And when I turn it off, the current that I can get is, I usually get few like tens of hundreds of nanoamps, or if the device is bad, only a few microamps. So still there is an order of magnitude difference, right? So let's say nanoamps is the current that I am getting. So this is what I am talking about, and for the breakdown I'll only focus on the off state. But I just explained the device is on. Just for the sake of completion, this term 2DEG you are seeing is also known as two-dimensional electron gas, and this is formed at the interface of aluminum gallium nitride and gallium nitride. I cannot go into the detail as to why it forms, will it form if I have a different material. I cannot go into that discussion, but this is very similar to the inversion layer. That's all I mean to say, okay. So this sets the background for the discussion on breakdown in these transistors, okay, right. So now what we have is, now based on this device, in the measurement of the 3-terminal breakdown of a GaN-HAM device. So this is very similar device for which I had introduced in the previous slide, okay. The compliance point. So when we are measuring, actually when we are measuring these devices, so how do we measure these devices actually? So this is a source, and I put a metal probe over here, okay. I put a metal probe over here. Let's say I'm calling this probe 1. I put a metal probe over here as well as over drain. Probe 2. That's how I'm providing these voltages. And the third probe is somewhere over here. Probe 3. And all these probes, probe 1, probe 2, probe 3, are connected in turn to a voltage source. Rather, what we call is source and measuring unit. So this is the terminal 1, right, and this is your terminal 2, and this is your terminal 3. And here there is a software, there is a user interface. So where here I can control what voltage to give to 1, what voltage to give to 3, and what voltage to give to 2. And also I can measure the currents, right, and this gives the data in terms of an Excel sheet, that V versus I, and there are various other things that you can play with. So essentially that's how I'm probing, and you can see that I am using 3 terminals, which 3 terminals naturally: gate, source, and drain. These are the 3 terminals which I'm probing. These are metal tips, How wide are they, you might ask? They are only I think around 20 microns in diameter, and this pad that you are seeing is only 100 microns. So these are very small devices that I'm talking about, which I fabricated for my work. Okay, so that's how we measure it. There's a machine which is giving electrical inputs in terms of voltages and also measuring the currents, right? And this gives us the data. That's how we are doing it. So with three terminal breakdown, now I hope you understand the term that why it's called three terminal breakdown of a Ganham device. The compliance point. So when do we say the device is broken down? There must be a limit, right? Because sometimes it can happen. I'll tell you what do we mean. How does the profile actually look like of current? Okay, something called compliance point, which I talk about. Which of the following statements is true? So let me just draw these. Let me just draw this diagram from the previous slide here. So we have this as grounded, right? And we have VG here and VD here. So what I can now measure, I can also measure ID and IG. Okay, so let's do that now. So what I'm going to do, I'm going to measure, and what is the thing that I'm going to change? So I put VG such that the electron gas is not there. So let's say if it's VG as minus 5 volts. What I'll do is now I'll sweep VD from, let's say, 1 to 100 volts. So on the x-axis I have VD. So see, if the drain voltage is 0, there should be no current. Even if you apply VG or don't apply VG, right? The current should not be there. I'll gradually increase the drain voltage. So this is let's say 10 volts, 20 volts, 50 volts, and let's say this is 100 volts. So I'm gradually increasing the drain voltage by fixing the gate voltage. Okay, so what will happen? Let's say this is I'm plotting here. Let's say ID, the drain current. Okay, how will it look like? So drain current, if you see, so drain current will be, how is the current coming from? The current cannot come from here, right? This is blocked. What can happen is that you can see its effect is not the depletion, the stem-sum pathway available. So what can happen is that electrons can now still go something like this. This is, we call the leakage path. This is the leakage path. The electron can still travel like this. Okay, and so what you can happen that if you increase the VD, the current can increase, still it can increase. Okay, so let's say from at 0 volts the current was here. At let's say 10 volts the current increased slightly. At 20 it increased even more. At 50 it was here, and let's say by 100 it was over here. So I'm drawing the ID. It will look, let's say, something like this. It increased very rapidly around 100, and on 100 let's say it has reached over here. Okay, I have to extend this, and let's say this point that I'm talking about is 1 milliamps. Why per mm? Because this device periphery also matters. Let's just forget about per mm. I'm just normalizing with respect to the length of the device. Okay, let's just the gate length actually. So let's just forget about the gate length for now. So let's say the absolute current that I'm getting here is the current value that I'm getting is 1 milliamps. Okay, 1 milliamps. Okay, the question asked that the threshold should be 10 microamps. So 10 microamps, and mind you, this is in log scale. Let's just forget about the log scale. It might lead to more confusion. It's in linear scale. Okay, I'm talking in linear scale, and this is then also I have to change this number. Just hold on a second. So this is let's say 100 microamps per mm. So where will the threshold line lie? Threshold line will lie somewhere over here. This is the threshold of 10 microamps per mm. Why did I choose this value? This you can choose arbitrarily. You want 10 microamps per mm, but the question asks that as soon as the drain current crosses this value, right, I have to say the device is broken down. Okay, so at what voltage did this device break down? If you see, this is the voltage over here. Let's say this voltage is 70 volts. So I'll say that for this device this device broke down at 70 volts when the gate bias was -5. That's how I'll say it. Okay, I told you one leakage path. There is actually one more leakage path. What can happen is now is just that you see there are various pathways that the current can also conduct over the surface, not just here also between drain and gate at the surface itself. Okay, so what can happen is that because see now you're increasing the drain voltage, so VDG is also increasing. Okay, so what can happen is that the gate current can also increase due to whatever reasons from here or from here, wherever. So I'll draw now IG in a different color now. Now I'm also drawing IG on the same plot. Okay, let's say my IG looks something like this. This is IG. So you see up to 100 volts. So I can only draw up to 100 because my instrument supports that I can only go up to VD equal to 100 volts. This is an old instrument. I cannot go beyond that. So this is how the IG will look like. Okay, in the red was your ID. Okay, this was your ID. So when do we say this device is broken down? One way of saying is that, okay, when the drain current crosses the threshold, it crossed at 70 volts. We can also say when the drain current crosses, when the gate current crosses the threshold. Gate current never crosses the threshold. So we'll say the breakdown voltage in terms of gate current is above 100 volts because it will cross at some point of time, but we did not measure it. So in this case, the device is broken down, the gate leakage has reached, right, and the drain current we can neglect. So I am neglecting the drain leakage here. This is correct, right? If the drain leakage is not there, only gate leakage is there, then you have reached the threshold limit. Alternately, what can happen if the gate leakage is negligible, that is the red curve only, right, and the drain current has reached has crossed the threshold, then again you will say the device is broken down. A third case is what it's more realistic. When you have both drain and gate leakage, how will the combined curve look like? ID plus IG. This will look something like this. If you add blue and purple curve, this is how it will look like. And now I'll say the device is broken down at here 50 volts. Okay, that's the third option. The device is broken down and the gate plus drain leakage has reached 10 microns. So this is the threshold. So when did you cross the threshold? At 50 volts. So this option is also correct. So that's how we define the breakdown of a device, three-terminal breakdown in this case of this particular device. And this, in fact, when we are making these devices, whether in the labs or in industry, this is of very primary importance. One is what is the breakdown voltage, and even before that, you must define some threshold. So industry defines some threshold for any particular current, for any particular technology. In this technology, let's say the threshold I'm defining is 10 microamps per mm, and thus the breakdown voltage is not 70, is not above 100, but actually only 50 volts. Okay, whether that will suit your needs or not, that's a secondary problem. You have to maybe improve your, for instance, you have to reduce this leakage path. So you have to do some material magic in the gallium nitride itself. Or maybe the leakage is at this interface between blue and green. You have to improve this interface. Or maybe the leakage is between over in this layer, in the green layer over here, right? So there are ways to improve, but one of the ways to characterize how good the device is to measure the three-terminal breakdown of this transistor. And this is how we do it. The three probes are at drain, source and gate, and this is how we measure it. Okay, right. Now I have just given you a brief introduction about the three-terminal characteristics or the off state, right? Now we'll go into the on state. How do these transistors work? So there are different, as we have seen, the transistors are just essentially three terminals, but the gate will control the flow of electrons between drain and source, or flow of current rather between drain and source. So there are various applications of these transistors. If you see the lecture, the memory devices, the logic devices, and here first I'm going to talk about what we call the power transistors. So as the name suggests, their main aim is something related to power. Okay, this means essentially here changing the mode of power. So for instance, that I'll tell you this, the DC converters, you see the DC to AC to DC you see very regularly. When you're charging a mobile phone or a laptop, what happens is that the socket in your house or in your room is your AC input, 220 volts in India, correct? Your mobile is being charged, let's say 5 volts. If you see the specifications on a mobile charger, let's say 5 volts. If you see, for instance, some laptops, for some laptops the charger was slightly heavier, 10 volts or 20 volts, right? So there is a power conversion that is happening. So that is being done using something called the power transistors. Okay, there's a DC to DC conversion. Sorry, that is very much required in electric vehicles. DC to AC, AC to DC, and so on. So this is one of the most primary applications of these power transistors. They're not just transistors. We make circuits out of these transistors, and they provide one specific application. Okay, what are the materials that we typically use? Silicon is invariably you will find everywhere. The primary reason for that is cost, because silicon technology is so much more mature. The physics of it is so very well known, not just of silicon, what kind of dopants you want to use, what are the fabrication techniques, the doping, how do you etch it. We'll talk about these techniques a bit later in today's session. But silicon technology is so much more mature, physics wise as well as technology wise. Hence the costs and does the costs remain minimal per device, per transistor, let's say. That's why you see the Moore's law kicking into effect. Okay, but there are some other technologies which are competing in a particular segment of application, even with silicon. So gallium nitride is one of them, and silicon carbide is another. This is, I'm talking specific to the field of power transistors. Okay, right. So in the previous slide on 3-terminal characteristics, this is the diagram that I have shown in on state, right? And just to repeat myself, so what happens is that even when the gate, this is the gate bias, even when the gate bias is 0, okay, you have just a second, you have a readily available source of electrons which are available at this interface. This is very similar to the inversion layer that we formed in a MOSFET. Okay, and if you apply a bias between drain and source, what you can have is you can have a flow of current, which is depicted by this. So these are the electrons, also known as two-dimensional electron gas, as I have written in the previous slide. Just give me a moment. Okay, so yeah, so this is the on state. And how will the on state look like? As I've been repeating myself over and over, is that this is very similar to what is happening. I know the fabrication is different. You have two layers. This also, alcan is also by the way known as a barrier layer. Okay, different reasons for that. We'll not go into that. But what essentially is happening, even though the epitaxial stack is different, because there it's only, you see the silicon and then there was an oxide, right? Here you can say the silicon counterpart is gallium nitride and the silicon dioxide counterpart is aluminum gallium nitride. There are other layers as well, but I am just trying to be as close to the MOSFET as possible, and at least you can appreciate that the nature of the behavior will be very similar to what we have in a MOSFET. So this is the output characteristics from your slide, I think from one of the slides of the MOSFET session. This is taken from that itself. I have not changed anything. I just copied it as it is. The only thing I had changed is this VT. Threshold voltage, if you recall, the way we defined the threshold voltage in MOSFET is when the inversion kicks in, strong inversion kicks in. Here you will say that, oh, the electron layer is already existing, right? And hence I am saying that even to have a bare minimal current, it will happen even when VGS is less than 0. Okay, but there is still a threshold voltage. If you recall the off characteristics that I had drawn, right? So let me draw the off characteristics here now. So the off characteristics will be, the off characteristics, I will deliberately draw it a bit high because it actually should coincide with the x-axis, but I'll not draw that because to illustrate that there is still some leakage current. Okay, to be more realistic, this is how this is when the device is, I'll say, cut off, or to be more clear, when VGS is less than VT. Okay, the threshold voltage here will be negative. As you can see, threshold voltage is when in the MOSFET it was when inversion layer started to form. Here the threshold voltage is where this sheet of electrons disappears, and you can see that the sheet of electrons will disappear only when I apply negative voltage. It's naturally present at Vg equal to 0. So if you apply, let's say, Vg equal to -1, some electrons will be repelled away below the gate. -2, more will be repelled. There will come a time when you will repel away all the electrons, right? And again, there's some compliance limit. So all those numbers, when you say it ceases to exist, it never happens. It's just that its concentration reduces to such a low number that the current is very small. It's the leakage current only, which I have drawn in red here. Okay, so this is the ID, which is below, when we are below the threshold. Okay, in this VDS. Rest, if you are above threshold, you see VGS, let's say, is above threshold. VGT is, let's say, -5. So -4, you will get this curve. -3, -2, -1, 0. You can go on further, right? But you can see that VGS equal to 0, there's some appreciable amount of current that is happening. Okay, so this is the output characteristics that of this particular, what we call it an HEMT, high electron mobility transistor. It has some advantages on MOSFET. I'll say that the key term here we're getting is mobility, right? Why the mobility of electron is high? The reason is that in silicon, when the inversion layer is between the oxide and the silicon interface, there are various ways of scattering of that electron. Impurity scattering, because silicon is doped. If you recall, it was a p-type silicon for an N MOSFET, correct? So there are some dopants which will scatter the electrons. Second, this is an interface between silicon dioxide and silicon. Although it's nearly close to ideal, there will be still some scattering, right? And there can some defects that might arise on that interface. It just so happens that the electrons over here are solely inside the gallium nitride, and they form a they form a quantum well. Okay, I cannot go into the details of that. That enhances the mobility of these transistors. Okay. The amount of electrons that are here they depend on the thickness of algan and the concentration of aluminum and various other factors. But the mobility of electrons in this HEMT, for instance, can be as high as 200. In the range of 2000s, while for silicon it's only up to 300 or 500 maybe at max. So it enhances the mobility, this kind of structure. Okay, so this is now the device is working fine, very well. Okay, but there's something at the very important parameter, right? There's a very important parameter that we talk about, is the on resistance. In power transistor, what you want these to switch on and off. Essentially, you want this over here. First, at one point I'll show what I mean. So essentially what you are doing, so essentially what you are doing is something like this. This is with respect to time. This is the gate voltage. So at one point of time you are applying Vg equal to 0 for some time, and then you're turning the device off. So this is -5 volts. Okay. For some time it's off. Then you want to turn it on again, then off, and then on again. So you want to continue this cycle. This is the switching thing that I was talking about, right? So this curve corresponds to Vg equal to 0, correct? And this corresponds to Vg equal to -5 volts. So you want to be switching, as far as ID is concerned, between these two curves. Okay, and when you are conducting the current, you want this point to be ideal. How does an ideal switch ID characteristic looks like? The characteristics of an ideal switch, they look something like this. Instant rise. Essentially, even for VDS equal to 0.001 millivolts, it will start conducting. But you can see it has taken certain amount of time, certain VDS SAT, which we have written here, to come here. If we increase the slope of this line, right, this means we are getting close to ideality. So we want the slope to be as high as possible. Okay, that slope is what we call our on resistance. Okay, how do I define it? It's simply delta dVDS over del IDS, or if you're talking about this curve, del IDS over del VDs. Essentially, you take the slope of this line. Slope of this line will give you R on. I repeat, I want this line to be as steep as possible. I also want these current levels to be high, but I told you they depend on the electron concentration and so on. Let's say I fixed that, right? But I still want this slope to be higher. So I want this to behave like an ideal switch. So when it's on, it will be like this, and off, it will be the red line that you see, the cutoff line. Okay. And this is the switching that I'm doing. So in the power transistor, this happens. This actually happens. You switch on and off, on and off, on and off periodically. Okay. You want R on, I repeat, as low as possible. That is, you want the slope of this line to be as high as possible. If R on is low, when will this be low? When the slope del IDS, del Y by del X, Y versus X is high, right? So what I will say that line to be as steep as possible. That's what you want. You want to reduce R on. You want this quantity to be as low as possible. In the on state I am talking about. So that's how an a good power transistor should work. Okay. Let's now talk about the off state, because remember, I am switching on and off. On I have talked about, very good, I want low R on. Let's talk about what, and I also want it faster. So essentially, if you recall the expression for MOSFET, the ID, right? Mu n C ox W by L Vg minus Vt whole square by 2. I'm talking about the current in saturation. So it depends on mobility also, correct? And so mobility, I told you, is usually higher for HEMTs rather than these your silicon MOSFET, silicon based MOSFETs, right? And there are various other parameters that are there. It's not like they're not there, but I just want to emphasize on this mobility part. So higher the mobility, essentially, higher should be your drain current, and Cox also, but mobility at least you can clearly see over there. W by L is just the geometrical dimension. So we normalize with respect to them, so they do not play as big a role. Okay. Second case now we are talking about is something called the off state. Okay. Second I'll talk about is the off state over here. So what we have is this is the same diagram from earlier, but the text here says the electrons concentrated in the 2D layer. Remember, there was a two-dimensional electron gas here, but now I am applying a negative potential. So what potential? Let's say, give us a number, Vg equal to minus 5 volts, and this is Vs. This is I am grounding this. This terminal is Vd. This is the setup that we had used to measure, if you recall, the 3-terminal breakdown voltage. Okay, and it says that the current ceases to flow, so the current will simply stop flowing. Well, actually that's not correct. We saw that there is some leakage current. There can be leakage path like this, through this. There are various pathways, and this is still open area of research that we try to minimize leakage pathways rather. Okay, so irrespective of that, there is some leakage current, correct? And so as I've told you, corresponding to the leakage current, there was some breakdown voltage. I'm just going to draw it here. The same thing, the same experiment that we had done here. So Vd, what I had done, you fix Vg and you sweep Vd from 0 to 100 volts, right? So this is 10, this is 20, this will be 50 over here, and finally 100 will be somewhere over here. And we saw, let's say for this device, the characteristics look something like this. Okay, and this is the threshold line. When the current crosses this value, we'll say the device is broken down. And we saw I'm using the same numbers, 10 microamps per mm, and correspondingly this came out to be 75 volts. I'm only drawing ID here, just to keep things simple, but if you recall, it was ID plus IG rather over there. Okay, so this is the drain current that we have. So 75 volts is the breakdown voltage for this particular device, and I'm not going to repeat myself again, but because we have talked about these breakdown, 3-terminal breakdown rather, in great detail. Okay. This is the compliance level. I'll again emphasize that you can choose the compliance level, but not arbitrarily. I mean, there must be some agreement among the people who are working in this field. So let's say I can choose the compliance to be, for instance, for some other technology, the compliance level is, let's say, 100 microamps per mm. Okay, that person will say, okay, my breakdown is 100 volts. That's correct, because whenever you're saying that the breakdown is this much, you must also say what is the compliance. That is very important. Okay, okay, all right. So we have talked about the off state, right. Well, let's come to a problem now. Sorry. Okay, so which of the following statements are true for power switching? I've already defined what do I mean by power switching. Essentially what I'm doing is, this is with respect to time, this is gate voltage. You are on here and you turn it off, turn it on again, turn it off. You can, I'm just choosing some arbitrary, this need not be square waves. Okay, so this is on, off, this is again off, on here, and so on and so forth. You can just continue with this. Okay, so there are two switches. Okay, switch A and switch B. Okay, and I'll write here the characteristics. What characteristics are we talking about? We are talking about R on. So what is the value for A? Is 5 ohms. For B, it's 10 ohms. Okay, that's the on state. In the off state, please remember, we talk about the leakage current, or concept related to leakage current is the breakdown voltage. So breakdown voltage is for device A is 400 volts, and for device B it's 600 volts. Okay, so now we have to see which device works better. One second. Okay, in the on state we have to compare. So remember, in the on state what we had talked about, we want R on to be as low as possible. Okay, so we want R on to be as low as possible. That means I'll choose this guy wins, device A wins. Breakdown voltage I want to be as high as possible. Why is that? Why is that the breakdown voltage should be as high as possible? When we talk about the power rating, there are various terms that are involved. It's the mathematically it's a bit more involved, but you can at least just say that it depends on the current, the on current, and the off voltage, which is the breakdown voltage. Okay, if you when will your I current be higher? You want this power rating to be as high as possible. When will the on current be higher? When the on resistance is lower. Okay, you want to increase this power rating, so I on should be as high as possible. This means R on should be as low as possible. That's why in device A and B, switch A and B, switch A wins. Okay, in terms of the breakdown voltage, now let's see. Breakdown voltage you want it at again as high as possible. So in this case, device B wins. Now this is a problem. Which device to choose? A is good and B. So let's just complete the problem for now, and then I'll come to the analysis. So among switch A, A operates better in on state. Correct. A will operate better. And among breakdown voltage is this. In the off state, right? In the off state, B will operate better. Switch B is better in the off state operation. So now we are stuck, and this is some realistic scenario. There are always trade-offs involved. Okay, there are always some trade-offs involved. In the on state something is good, and off state it's bad. So what to do? Which one to choose? So this is we'll talk how to choose which material systems rather, because let's say these two are two different material systems. This is material, switch A is made of material X and switch B is made of material Y, or material system rather, because like in the HEMS we have been talking about material system. We are talking about gallium nitride based HEMS, or rather GaN HEMS, aluminum gallium nitride based HEMS, right? And let's say device A is some other technology. Okay, so here for a given technology or for a given material system, how do we compare them? We compare them with something called the Baliga Figure of Merit. So here again these are the same two what do you call, two schematics from your on and off states. This is your on state, this is your off state, and which are the parameters that we called about in the on state. In the on state, remember, we had R on, that is the parameter we are focusing. In the off state we are focusing on breakdown voltage, VBR. Alright, okay, so how are they related? They are related by this expression, and as you can see that these are the numbers which we can expect. These are some ideal numbers, but they are dependent on the mobility. So we're talking about only electrons, where the electrons are the conductors. So that's why you see mu n, mobility of the conductors, times EC. EC is nothing but the critical field of this particular material we are talking about. For instance, for gallium nitride, this is 3 megavolts per centimeter. Okay, for different material systems, it is different. Now, what we can do is we can plot. We'll try to plot R on versus breakdown voltage, right? And let's just try to see how it behaves. So, for instance, for any given, let me just plot this first. So, in this plot, what we are seeing is, let's just focus on silicon for now. Okay, focus only on silicon. This is the silicon limit. So, essentially, ideally, this is the ideal silicon line, because for silicon, epsilon s will be fixed, mu n will be fixed, and EC will be fixed. So the product of R on times breakdown voltage square, R on divided by breakdown voltage square will be a constant. This constant is this straight line that you see over here. Okay, but let's say you increase, the EC, right? If you increase the EC, what's going to happen is this curve will shift to the right, and let's say you get the GaN, because GaN has higher critical electric field. So this is among other reasons, that's why you see the GaN limit this is the theoretical limit. You cannot have larger than that. Okay, so what we see is that, now let's compare now I'll put some numbers. So when we say we are talking about this on resistance, okay, for this on resistance, a silicon based device will have the breakdown voltage of somewhere over here, 80 volts. If I want this much on resistance, a gallium nitride based device on the other hand will have breakdown voltage over here. This is around 400 volts. This is the difference. Same on, so on behavior is the same, but off behavior has improved drastically. Okay, let's see the other side. I want breakdown voltage to be 100 volts. Okay, I want breakdown voltage to be 100 volts. So which material to choose? Let's see. If you want breakdown material to be breakdown voltage to be 100, for silicon, it will be, this is what, 2 milliohms cm minus 2, sorry, centimeter square. This is just normalized with respect to area. Okay, what about the gallium nitride? So gallium nitride, we want, it will not be visible in this plot. You see this line, you have to extend it all the way over here, so it will be much lower. So for gallium, this is for silicon. For gallium nitride, it will be, I don't know, maybe a few nano ohms per centimeter square, orders of magnitude difference. Okay, this establishes that theoretically, at least, gallium nitride is a much better material system than silicon. I said theoretically, and that's why I'll come to the first point where I talked about the different materials like silicon or gallium nitride or silicon carbide. That's where silicon maturity comes into the picture. Okay, gallium nitride is not mature a field as silicon, physics as well as technology. Hence, even though theoretically it's promising, that's why you see this desired direction plot from this author over here, and we want to go into this direction. This is, by the way, for power transistors. There are different figures of merit for other transistors also, but for power transistors we want to go into this direction, and hence you can see theoretically at least silicon, gallium nitride is a much better candidate than silicon. How are they related? This is actually the fundamental limit for any particular material system. So for silicon, that you're seeing all the points, for instance, when you're seeing this point that R on is 10 to the power minus 2, put this value here, breakdown voltage is this 200, you put this value over here, and and then you can rather you put these numbers here and you put R on is 10 to the power minus 2, and you will get this point. Similarly, you put R on equal to 10 to the power minus 3, you will get this point. That's how this straight line was populated. Okay, so this is how I just wanted to illustrate that how are different material systems related to each other. How do you choose which device, which material to choose to form a particular device, okay, for particular application. So this is how we do that. Okay, this is a problem, I mean, I have talked about it in the previous slide itself, but just to give in terms of numbers, that's how I put this. Which of the following statements are true for power switching, assuming ideal material properties for GaN and silicon? Now this is where the thing comes in, ideal. GaN is still not ideal. I would say will not achieve that in any time, but the workarounds for silicon, the technology for silicon is much more mature. Okay, that's why you get much cheaper electronics, and functionality wise also they are acceptable. Okay, but let's now, for the sake of this problem, discuss the ideal properties, ideal gallium nitride versus ideal silicon. That's why defect free, perfect growth, etc., etc. So what are we talking about here? We're talking about breakdown voltage and on resistance. Again, same thing. So let's do this over here. It's the same plot from the previous slide, by the way. So what are we talking about here? So okay, again just the comparison. So again I'll draw that chart. So first is the characteristics, right, and then we have silicon, and then we have gallium nitride, just like so. We have R on here, and we have breakdown voltage here. Okay, so what is the we have been given, 1 second. Okay, so we will take a different route in this case. Fine, let's do the option 1 first. So option 1 says silicon gallium nitride both have the breakdown voltage of 600 volts. So let's find the breakdown voltage 600. This is 2, 3, 4, 5, 6. So 600 will be here. This is 600 volts, right? Which will have the better on-state performance. So on-state performance means which will have the lower R-on resistance. So at this point, the gallium nitride is below 10 to the power minus 4. So for this option, I will say for gallium nitride is less than 10 to the power minus 4. For silicon, same option. At this, you have to, this is the point that you will get. Okay, so let me say it's this is 0.1, so this is, let's say, 0.05, 5 into 10 to the power minus 2 ohms centimeter square, same numbers. Which has the lower resistance? Gallium nitride has the lower resistance, right? For the same breakdown voltage, silicon point is here, gallium nitride point is here. Which is better? Gallium nitride. Okay, this option is correct. So on performance of gallium nitride is better. This option is wrong. Second case, what we have now is we have been given, this time we have been given the on state resistance. Okay, so let's say the on state resistance, how should I do this? Okay, let's say the number that I'm talking about is here. I know this is not the same number as this, but this is a different plot, but that's fine. My argument will stand. So along this line, along this point, we'll move in the x-axis because we want to know what is the breakdown voltage. So the breakdown voltage for silicon would be over here. This is silicon. For gallium nitride, it will be over here. What is the breakdown voltage in silicon? So for silicon, it is, let's say, 100 volts. For gallium nitride, this same number is around few thousands, right? Let's say 5,000, 7,000 volts. Which one is better? I told you, the higher the breakdown voltage, the better it is. Okay, so if both have the same on resistance, performance, off-state performance of gallium nitride is better. This is the option. Okay, let me just see whether I'm correct or not. At the same breakdown voltage of 600 volts, so we have this breakdown voltage of 600, which one has on-state performance? Silicon is here, gallium nitride is, it's not even, I mean, it's below less than 10 to the minus 4, whatever the units are. Similarly, when we are given the on-state resistance over here, the off-state performance of gallium nitride is much better, right? Because you will traverse parallel to the x-axis. When you are given the breakdown voltage, you traverse parallel to the y-axis. That's how you find out where you lie on this plot. Actually, when the researchers or when the industry, they put out their number, they'll say, oh we have close, we are at this point, we are achieved close to very silicon limit. Some of the scientists will say, oh no, we are here, we are very close to silicon limit. And when we start off our results, we are somewhere over here, very far away from the. But silicon is, we are very close to the silicon limit. For gallium nitride, it's not the case. For instance, gallium nitride, maybe we are only over here, let's say. Still far away to go, or here. These are the data points for gallium nitride. This is the gallium nitride. Okay, and in the green you have is So all these data points that I'm seeing, these are experimental, okay, on silicon. These are experimental gallium nitride. The theoretical limit is the straight line that you see over here. We want to be as close. We want to be as close to the theoretical line as possible, naturally. Okay. Okay. So that ends the discussions for the power transistors, right? The another application that we have of these devices, the semiconductor physics that we had talked about, and now the devices is telecommunication. Essentially, you're using your mobile phones for, I believe, at least your adult life. Okay, that's a mobile phone technology that you're using. Now you have 5G phones, and some countries have 6Gs in their cities, metro cities at least. So that's telecommunication, mobile communication technology. The other is your radar communication. You are receiving your direct to home cable channels that you have, right? How is it coming from? It's coming from a satellite. Okay, you see those dishes on rooftops and whatnot. And to be more sophisticated is how does the deep space communication happen? When Chandrayaan went, when Mangalyaan went, how are they communicating? That's radar communication. Okay, the frequencies differ, yes, but what I'm just saying, the radar communication happens to be done by the transistor circuits. In the circuits, the building blocks that we have are the transistors. These transistors are used for radio frequency communications. These are called RF transistors. Radio frequency. RF stands for radio frequency. I'm talking about radio frequency over here. And again, there are different material classes. Silicon will always, very rarely you find a field in semiconductors which does not say, okay, silicon is not there. It's there. I repeated it over and over again due to the cost and the technological maturity. Okay, gallium arsenide is there, gallium nitride again is there. Actually, my work is predominantly my research work is on gallium nitride based devices, RF transistors rather. So this is which I work on extensively. All right. So when we talk about radio frequency, what frequencies are we talking about? So what we have done is that there is an international telecommunication union, ITU, I believe I'm saying it correctly. So they have created different bands. Okay, so for 1 to 2 gigahertz, what we call is the L band. I think 2 to 4 is S band, 4 to 6 I think is C, and then or I think it's 8. I'm forgetting. 8 to 12 is your X, and there are other various bands that we have. So 5Gs that you see, that I think lies somewhere in the C band. It's around 5 gigahertz or something. There is another in around 28 gigahertz also. So there are different bands of signal. These are the signal that is signal frequency. Since the radio frequency that I'm talking about, these are the frequencies that which I'm talking. Okay. Right. So what is this primary use? Is they are used as amplifiers. So why do we need that? So for instance, when you are speaking over when you are on a SIM call, not your calls on through various applications, but I'm talking about the SIM call, the mobile SIM call that you make. Your voice has to go out at your voice signal will travel at a certain frequency. It's a transmitter. Essentially, in your phone, a transmitter is fitted at that particular frequency. Okay, but the power and it has to go to a base station. The towers that you see, those red colored with all those dishes on them, it has to go there, and then it will be routed to the person you want to talk to. Okay, so you want a signal to have sufficient strength because it needs to travel a certain amount of distance to reach to the tower. Okay, it needs to be boosted. It's amplification. Okay, and similarly, when the signal is received, again it might be weak. You want to boost it, and even in the base station or the towers that you have, this is an application that is very. This is one of the most important functions. Rather, you have to amplify this signal. Okay, it's an amplifier, and this PA stands for a power amplifier. You must have seen this symbol. This is what some people might recall. This is an operational amplifier symbol. Sorry, right? 741. Right. Similar principle is happening here. We input some power. This is an RF power. Okay, that's why this P in RF. And we operate some DC power, we input some DC power. Why DC power? Because see, this is a transistor, it must have some VDD or the bias levels, the ground lines and all that. It needs to be there to operate this circuit or even a transistor for that matter. Okay, hence it requires some DC power, and it will amplify the power, and what we get is the output power. Okay, right? So output power, there are certain terms involved in this. I should write them here where I have space. Right, there's something called the drain efficiency. Drain efficiency. See, output we are taking on the drain side. Please note that. Do I have this in? Yeah, do I have this? Okay, fine. So this is your what do you say? The output IV characteristic. So this is IDS versus VDS. And again, these are your various gate biases that you see over here. On this point, this is your VGS. Input signal is nothing but VGS over here. You're swinging the gate voltage, right? And when you're swinging the gate voltage, essentially, so this is your bias point. This is a DC bias point, essentially. Okay, this is, let's say you are putting VGS equal to remember, threshold voltage are taken -5, right? So let's say VGS over here, I'm putting it as -2 volts, and on top of that there is a swing. So let's say this swing is from this will go to -1, and let's say this will go to -3. Okay, so the swing is from -1 to -3. VGS is swinging from -1 to -3. If VGS -1, you know the current should increase, right? Because this top point is VGS equal to 0, and somewhere over here is VGS equal to -5, the cutoff point that we had talked about. This is the threshold VTH. Okay, right. So we are swinging between -1 and -3. The input voltage is swinging between -1 and -3. Correspondingly, the IDS will take this plot. I'll mark it as I high, let's say, right, and this point I'll mark this as I low. Again, this is the output signal. Output signal is swing something like this, corresponding to the input signal. This is the output signal, IDS output signal. Okay, you're seeing, okay, but so where is amplification? So essentially you put a load, that is again a different thing, which load value to choose. Essentially you must be aware that I'm forgetting the name, that load should be the for most efficient power to be delivered, the maximum power to be delivered, this load value magnitude should be equal to the output value of the output conductance of the transistor. Same thing we are doing here. Okay, so how to select the load, that's a separate thing, but what I'm seeing is that this is the current. This current is being supplied to a load, and there you will get the V output. Okay, and essentially I square R is essentially your output power. Okay, that's the output power I'm talking about. So as I was saying, this is taken from the output is usually taken from the drain. So the drain efficiency will be simply be P out divided by P in. Oh, sorry, I mean I did not. Okay, so there are different ways of expressing that. The way we usually express these is in dB. Okay, the way we typically express is in dB, decibels. Okay, so what we see is I can say is that P out dB minus P in dB. That depends on what units you are choosing. So this might come in denominator if you are talking in watts. Okay, right, but there is a more, you can see you are adding a power here, right? Correct. So a more, the term which is more frequently used, I might be wrong on this section, I am mistaken. Let's not talk about drain efficiency now. I'll stick to which is encompasses rather the true sense of this amplifier. So what is the power added efficiency? Power added efficiency is nothing but P out, the output power, minus P in. This is the power you are adding. over PDC. You're also supplying some DC power. Okay. This is the power added efficiency. Again, where you are biasing, there is various fields. So where you are biasing, so currently I am biasing. This is the load line, the red double-headed arrow that you see is what we call the load line, and you can see that I am right in the middle of the load line, right? So here I can have the maximum swing, correct? So there are various terms that are there. For instance, efficiency, which I have written over here. The other term we call is the linearity. Linearity means now you can see it's linear. This is also sinusoid, this is also sinusoid, the same frequency, correct? Ideally it's like this. When I'm biasing it here, if I bias it here, you see the input signal will be sinusoid, but the output signal will be clipped, because only one half of the cycle will be contributing to the current. There the linearity is not there. It's only because it's sinusoidal in one half, not sinusoidal in the other. So linear means y equal to mx. It's not following that line. Or fx, gx equal to k times fx rather. Okay, that's what I mean by linearity, right? And the other factor is gain, which depends on various parameters. But these are a few parameters, what's called the figures of merit, or when making a device, when we are measuring the power out of it, these are the three things which we typically talk about. And power rate efficiencies, I believe, is one of the most important metrics. P out minus P in, that is the power you are adding, that is the gain that you are getting over PDC. So essentially how efficient it is. If you are using if you are gaining, let's say 80 units by supplying 100 units of power, fine, very good efficiency. If you are getting a gain of 1 unit of power by supplying 100 units of DC power, it's not efficient. Okay, that's why essentially your battery is being discharged in this, because it has to power this amplifier. Okay, there are various reasons, but I'm just saying that where this DC power is coming from in your mobile handset is coming from your battery. Okay, and it is being used in the transmitter, uses this DC power to amplify the signal that it's going to send out to the base station. That's how it typically works. Okay, right. So after this, okay, so I have a problem with respect to this RF transistors. So which of the following statements are true in respect of transistors used for RF power amplification? That is the one that I have been talking about. This is the power amplification I'm talking about. And this frequency of switching that we're talking about is in the radio frequency range. I mean, there are other bands also, KU, KA, K, and W and whatnot. But I just gave some idea over here. Okay. So please consider terminologies for saturation and cutoff related to MOSFETs and not BJTs. Yeah, so this is an assumption that I'm making, that since I've been talking about HEMTs, right, high electron mobility transistors based on gallium nitride. So I've already told you that their output characteristics looks very similar to the output characteristic of the MOSFET, which is seen in the, I believe, the 8th or 7th session, right? So here again we'll restrict ourselves to similar to the output characteristics, similar to the MOSFET, which is the same analysis on which I based my discussion of RF transistors on. Okay, right. So first option is a transistor with FT. There's something called FT apparently, gives better performance. So this is a performance matrices that we have talked, that the gain and efficiency I talked a bit about. Okay, so now the application is saying it's a radar system we want to operate at 70 gigahertz. Which transistor will you choose, which has an FT of 100 gigahertz or an FT of 200 gigahertz? Okay. Second thing we are talking about is for a given biasing arrangement, that is load resistance, a transistor with knee voltage of 2 volts, so and a breakdown voltage of 55 volts. Okay, so I should say, what do you mean by knee voltage? You see this curve here, this is known as a knee voltage. So this is the V knee. And why breakdown? Because essentially it's IDS. If you keep increasing the drain voltage, ultimately the device will break down, correct? So something like this. I'm not drawing them in more detail here, but let's say this is the V breakdown. So you must operate your device can only be operated in this range, correct? The drain bias that you can apply is only this much. Okay, please note that. Fine. Or rather, the output voltage that you can get, output voltage can only swing between these two extremes. All right, and this is the knee voltage of 2 volts and breakdown voltage 55 volts, has a maximum output power rating. So how do I get the power rating? We'll talk in a bit. And so these are the two terminologies that we are seeing here. One is the FT, the other is output power, maximum output power. Okay, essentially this, you want to maximize this, and this is maximized when we have the load matching to be happen. Let's say the load matching is there. That's why this question says at for a given biasing arrangement. So we'll assume that this biasing arrangement is good enough that we're getting the maximum power out. Okay, so just like we had a Baliga figure of merit for power transistors, please remember that there we had to balance the two things, which is the on resistance, right, and the second thing was the breakdown voltage or the leakage current that we had essentially. Okay, here the two things that I want to balance is again the breakdown voltage, which is, please remember, depends on the critical field. So critical field is when your bonds will start to break for any given material, right? So breakdown voltage is essentially this is voltage, so E critical times your distance that the field is being applied is the breakdown. It's fairly straightforward. FT is something what we call as the unity current gain frequency. So I've been talking about power throughout here. There are two terms, the two frequencies that are involved here. One is called the FT, the other is called the Fmax. FT is the unity current gain frequency. Unity means when the current gain becomes equal to 1. This is the unity power gain, when the power gain becomes equal to 1. FT and Fmax. So just to how it looks like, they go something like this. This is the Bode plots that you may have seen. So this is, let's say, gain, and this is, let's say, frequency in hertz or gigahertz in this case. Okay, this gain is in dB. Okay, so when the gain in dB, this means when it crosses 0, that's when gain will become 1. So there are different types of gains we can extract for unity current gain and power gain. I will not go into that, but just understand there are two frequencies that are used to characterize RF transistors, FT and Fmax. Right, higher the FT. Essentially, FT is, please recall that, where do I have space? Okay, I'll draw it here. Okay, so what we have essentially is gate, source and drain, and these are the electrons that are there. This is the gate length, right? An electron has to traverse from one side to the other. So essentially, how fast is it able to transit? That's the velocity, right? Sim gate length divided by the transit time tau, and this tau is FT is nothing but 1 over tau. So how fast you are is been given by the frequency. Because the faster if in a material system the transit time is smaller, right, and you can see the LG has to be same for both of them. And similarly, V breakdown as I was seeing is E critical, right, times your distance. So this distance of breakdown is essentially sorry, the gate is over here, right. So essentially what's going to happen is the electrons will come and grow from under this. So the electrons at max will have to traverse this LG. Okay, and this VBR is essentially the breakdown voltage. So this breakdown can happen over here, let's say. So ECR into LG, and from there you get, this is the saturation velocity essentially. So from here you can just, if you eliminate the LG from this expression, LG is VBR over ECR, and you can very easy, you can quickly obtain this expression. So this is the LG is essentially when depleting, you are depleting only below the gate, not in these source gate regions and gate drain regions. Okay, hence the term that we should be concerned about is LG. There are other various parameters. So for instance, if LG becomes very small, there are short channel effects and whatnot. We'll not go into that. We'll just stick to the very basics of of of, this FT, unity current gain frequency. And again, as I told you, there are different material systems that we have. So you have the silicon over here, and indium phosphide is another, gallium nitride is inherently depends on the critical field and the saturation velocity of a given system. GaN again scores higher than silicon. Okay, so for both power transistors and for RF transistors, gallium nitride theoretically is better. And but you can also see, as I was saying in the previous slide. So what you see is that this for silicon they're very close to the theoretical limit, but there's still some gap to go between the experimental results, which are squares here, and the theoretical limit for gallium nitride. So that's when a technology matures. That's how it comes. So the devices that we typically get for silicon is your HBTs, and HBTs are also there for indium phosphide as well. It's not that they are only for silicon, but sorry, not HBTs, LDMOS, and there are other few devices which are there for silicon. For indium phosphide we have the HBTs, and for gallium nitride we have the HEMS. The various flavors of HEMS that are there. Silicon, obviously MOSFET is always there. I'm not saying MOSFET is not there, but yeah, so these silicon germanium HBTs are there. There's some gallium arsenide HBTs, and this is just the table you have. Okay, so now this is how it's like previous slide. For Baliga figure of merit, we have on resistance versus the breakdown voltage. So this is the off characteristics now here. This is the on characteristics for Johnson figure of merit plot. Okay, so let's do that. We have FT of 100 gigahertz, right, versus FT for 200 gigahertz, right. This cannot be explained through this, by the way, but you can see is that because the gain, as I've told you, that the gain falls something like this. Okay, so let's say one is saying okay, I'll try to do it here. So this is your gain and this is your frequency. Okay, you want a system to be operating at 70 gigahertz. Okay, so this is device 1. It has the cutoff frequency of 100 gigahertz. Another device, okay, another device has 200 gigahertz, I believe. Yeah, so another device has 200 gigahertz. So its performance, let's say, is something like this, right? And you want to be operating at 7. This is your point of operation of radar. That's what it's given, 70 gigahertz. Which is better? This gain is better, right? So what you want is that you want a higher FT device, simple as that. So transistor with FT of 100 gigahertz, no, does not have better performance. Is at a worse performance. So transistor 200 will figure better. It will have higher gain essentially, because the gain again I'm assuming the slope of this is the same. That is this is the same the Bode plot. You assume one pole and so on, right? So I'm assuming both of the slope is the same. So naturally the performance will be better for your 200 gigahertz FT device. Okay. Second thing what we talk about here is power. So power, I believe it was, yeah, so it's proportional to its V breakdown minus V mean whole squared. I think there is a resistance term also somewhere, because yeah. So what we have over here is okay, so there are two devices, both have the new voltage of 2 volts, but one has a breakdown voltage 55, the other has a breakdown voltage of 100. Okay, so essentially if you have higher breakdown voltage, you can have higher output power, simple as that, because now the swing is more. Remember this, where was it? Yeah, here. So if this breakdown is shifted to the right, your bias point can also move a bit towards the right, and you can extract more power out of the same device just because the breakdown voltage is high. You shift your bias point, obviously, right? And so that's what we are doing here, right? The higher the breakdown voltage, the better will be, the higher will be the output power. So for a given biasing arrangement has a higher, no, the other one has higher one. The transistor will have a lower yes, so this will be the correct option. Okay, so so this completes our, I believe, yes, this completes our analysis on the two flavors of transistors that we had talked about. One is the power transistors. In both of these, and RF transistors, in both of these transistors, I had predominantly based my discussion on a particular type of gallium nitride, which is a compound semiconductor, gallium nitride based transistors, right? The one field was power transistors, the other was RF transistors. And I'll come to this, I hope I recall that. I'll again come to the difference, that what makes it a power transistor or RF transistors. There are some mechanisms like how much leakage you are getting and what is the primary purpose. So based on what the primary purpose is, that's how you design. For instance, the gate lengths that we talk about in case of RF transistors, they are really small, and by really small I mean 100 nanometers or even smaller. For instance, the device which I have myself made has an FT of, I believe, around 50 gigahertz, okay, and it has a gate length of 200 nanometers, okay. There was a senior of mine who had made a device, I think its FT was, I believe, I'm forgetting the number, it was hundreds of gigahertz, and the gate length I believe was around 40 nanometers or something, or maybe even smaller. I'm not able to recall these numbers, but typically as you scale your gate length, because essentially now you have to travel smaller amount of distance for a given VSAT, if you reduce LG, right, the tau should decrease. If your tau decreases, your frequency increases. For a given material system, both of us had gallium nitride devices, gallium nitride based devices. So if you scale down gate length, your FT will increase. But there are other problems, that fabrication challenges which come when you talk about this smaller gate length. Okay, now based on that is a good point to just cue. Now we'll be talking about is, we have talked about this, okay, I told you 200 nanometer gate length, 40 nanometer gate length, this much thickness of silicon dioxide, you dope, say, source and drain in a MOSFET N plus type. How do you do that? Because these are devices that are in our phones that have been in the market for now, in some cases decades, right? How are they fabricated? We're not going to talk about testing or characterization, but how are they fabricated? What are some basic techniques? And in fact, at ISC we have this clean room. It's a facility which is it's a research grade facility. Industry has much higher standards, but we have these similar machines, similar equipments which are used to fabricate the devices that are commercially available here. The transistors, I told you myself, I made one of those transistors, right? Okay, so now let's talk about this problem over here. A process engineer is designing a PMOS transistor for high-speed digital logic. As I told you, the logic and memory devices I have not talked about here. That was not my area of expertise, but these are the applications, semiconductor-based devices. These are used. For instance, when you're playing a mobile game with high graphics, there's a lot of computations that are happening behind the scenes. You need digital logic for that, right? Your memories, now you can store I don't know, 3264 GBs of data in your mobile phone itself, right? So that's a memory, it needs to be stored. The laptops hard drives have 1 TB, 2 TB, even higher maybe, right? So these are based on semiconductor based devices only, right? I digress, sorry. So now for this application, for this logic application, it's required that it requires a silicon dioxide passivation. Okay, so for this characterization part, we'll be focusing on silicon technologies. So silicon and silicon dioxide, not gallium nitride. Okay, because the technologies for silicon and silicon dioxide are much more mature, as I told you. So we'll pivot back to silicon and its family. Okay, right. Which method should we adopt for 1 micron thick SiO2 passivation? So we want to passivate. So what is passivation essentially? So passivation is, put very bluntly, so let's say this is source, this is your drain, this is your gate, right? And what you have is, you want to protect this. So this is the metal contact, let's say, that we have. And this is one more metal contact that we have. You want to protect the rest of this area, right? Let's say at least this area. So you deposit some silicon dioxide on top of it. okay, to pass it to just so that this leakage mechanism, this surface I want to remain it as pristine as possible. That's what we mean by passivate. Passivate essentially at the surface, you know, their bonds are dangling bonds because it's a crystal that we are growing, and all of a sudden it ends up abruptly. So those valencies are not satisfied, right? What we do is that we deposit some material, some dielectric like SiO2, silicon dioxide or silicon nitride, to passivate the valencies of those dangling bonds. That's essentially passivation, what passivation means. Because they can have sometimes a detrimental effect to your device, especially the breakdown characteristics. Okay, so now what we want to do, we want to passivate. So I am just going to draw a passivation layer. Okay, so this is, let's say, substrate silicon, and I want to grow SiO2. I want to we want only, I know this thickness is 1 microns. Okay, so this is for passivation purpose. This is not as a gate dielectric. It has a different utility. This is for passivation. So what methods should we use? So there are 4 methods that are given: the oxidation methods and the sputtering or evaporation. So these are what are typically called the physical vapor deposition. What it means is that physical vapor, we'll come to that, but I'll just give a brief idea. Let's say you have some source in a crucible, some SiO2 is sitting, and your sample is over here suspended. This is all happening in a vacuum chamber. This is the gases that to pump. Okay, so what you do is that in evaporation, this is actually more centered. So somehow you evaporate this material, right, and this will and line of sight and to deposit on this substrate, on this sample. This is evaporation. Sputtering is that you have argon gas here, argon ions. Argon ions will bombard this, and physically this method, the SiO2 material that we have will be chipped away, and it will get deposited over here, right? So what we see is that the physical vapor deposition for this specific purpose, the quality is a bit inferior. Okay, and plus we want 1 microns. These are for lower thicknesses. These are good. Few tens of microns, hundreds of tens of microns. This is good. This can work. For higher, it may not. So for that, we go to chemical vapor deposition. Okay, these are okay. So what are these dry and wet oxidation? So essentially a substrate is sitting over here. Again, this is happening in a chamber, something like this. This is your in gas and this is your out, and this is heated usually at some, we do it at some very wet temperature. Second thing is that this physical vapor deposition is typically room temperature, by the way, and the oxidations that we have are hundreds of degrees, 800, 900, even higher, maybe 1200. That depends on the application that we have. So here we want to grow SiO2 on this sample. SiO2 on this sample. So what you do is that you need some gases which are called the precursor gases. So if the precursor gas is, let's say, oxygen only or oxygen, we call this dry oxidation. For wet, we flow H2O. Essentially these gases will come on the surface, they'll dissociate, and this oxygen, the silicon that is there, will be consumed to form SiO2. Okay. Dry oxidation rate is what we call is slightly smaller, and it's much better for when you have thinner growths. Okay, let's say a few hundreds of nanometers for this, and plus the quality is much better. So this quality is superior here. We want this only for passivation. Okay, so we want, even if some defects are there, we can live with that. Hence, we'll prefer wet oxidation, just because it's higher thickness, and secondly, it's for passivation. We can live with some defects. Okay, for a gate dielectric, because it's thinner, it's only a few nanometers, 5 nanometers or 10 nanometers, right? If it's a gate dielectric, right, then I'll definitely go for dry oxidation. But for this specific application, okay, I'll choose wet oxidation. Simple as that. Alright. Okay. Another process engineer now wants NMOS transistors for again high speed logic. Which method should he adopt for an isotropic doping of channel? Alright, so we want to dope something. So you understand the concept of doping really well. Intrinsic, let's say silicon, it has 10 to the power 10 electrons and holes per centimeter cube, right? And you dope it, you can increase the number of electrons if you dope it n time and so on. Okay, how do we do it? So there are two ways of doing that, primarily diffusion and implantation. So what you do is that, so you put, so again this is your substrate, silicon, let's say, and let's say you bring some species, the diffusion species that what you want to diffuse close to this. So let's say this is some material of some phosphorus compounded some precursor X. What happens is that the phosphorus comes over at this surface, and remember this is, it has some thickness, this material, right? Let's say it is 1 mm thick, and you want to diffuse it to certain length. So you bring this here, you keep this in an evacuated chamber. Again this is pumping out, there is some in gases obviously, right? This is happening, and you diffuse and you let it there are different mechanisms essentially. There's some species which you want to be diffused at this surface, and you operate it at, let's say, 1000 degrees Celsius. At this rate, there's a concentration gradient. At the surface is high amount of phosphorus, and in the bulk there is negligible amount of phosphorus, right? So phosphorus will diffuse. Now some phosphorus will come in. As time progresses now, the phosphorus start to diffuse here also. Why? Because it doesn't care about the direction. It only says, okay, my concentration is high here and my concentration is low here. So even though I have not exposed it, I want to do only selective phosphorus. So let's say I had this some kind of a mask here. Mask means I want phosphorus only here in this region, right? Phosphorus will come here, right? Fine, after some time. So it's abundantly here. What will happen? So this is your silicon substrate. This is silicon, and this was your chamber, right? This is silicon, this is mask. You don't want phosphorus to be in these regions. You want to protect it for whatever reasons. For instance, remember source drain, we only had in n plus only in source and drain, not in gate, right? How you do that? You make some masks. Okay, so let's say it has now become mildly n type because we are doping phosphorus, right? And what if we increase, if you keep the temperature is elevated, let's say 1000 degrees Celsius, what will happen? It says this phosphorus atom will say, oh, its concentration is very low here, so they will start migrating, diffusing rather, in this direction. What profile are you seeing? Let me draw it in a different color. The profile you're seeing of phosphorus is something like this. The number can vary. I'm not saying it will be uniform throughout. True, right? In fact, there are two ways in which it behaves, but its concentration might go something like this. This is from the surface, so distance from surface, and is the phosphorus concentration in centimeter mine. Let's say it behaves like this, right? I'm only talking about this distance x. Okay, I'm not talking about laterally, but laterally you'll also see diffusion. So this means the mask will not be that impactful, because this is known as isotropic, in the same direction. Iso means same, tropic I believe must mean something close to direction. So isotropic behavior, you are seeing the phosphorus atoms diffusing all the way, all across, with minimal control. Second, so this is diffusion mechanism. Okay, another mechanism to dope is ion implantation. So what happens in that is, so I'll draw it here. So we just say that on the right is your diffusion, is your discussion on diffusion. On the left, what we have is ion implantation. Ion implantation. What you do is that, again, let's take the similar material. We have silicon and we have these masks. So this is mask and this is silicon. So what's going to happen is you are going to bombard some phosphorus ions, let's say, and they'll get embedded. Simple as that. That's how it works. It damages, in order to activate them properly, you annihilate it, so it will have some diffusion. Yes, true. When you annihilate, this means to reduce the damage and diffuse them, but it will not have such a prominent effect. Its profile might look something like this. Some taper, but still not like this. The curves prominent that you see, it's highly directional. This is directional or anisotropic implant. Diffusion. Okay, sorry, doping. Anisotropic or directional doping, that's what it's called. It's not happening in the regions which are hidden by the mask. Okay, but we want isotropic for this problem. So what we'll go ahead is we'll say for this particular solution, for this particular problem, we'll choose the diffusion method. Okay, next, in a transistor we want to make some gate contacts. So I told you the contacts, Schottky contacts, we have talked about this. We want conformal metal layer. What does this mean? So again, let me just, so what you have is, this is the surface, this is your mask, this is your mask, and let's say this is your gate, and you want to deposit a metal. Okay, what does conformal mean? Conformal means it will hug the shape of the mask. So this is what is known as a conformal, or another term is good step coverage. You see that these two steps, they are covered even when I'm depositing this metal which is in green. Okay, I don't want to deposit metal over here. I want only where the gate is. So let's say the source and drain were here. I don't want the gate metal to be on source and drain. It will be shorted, right? I don't want that. I want only on top of gate. So that's, I will choose this kind of I'll choose, this is the conformal one. Okay, right. The other kind of mechanisms, I'll again, same structure. This is your gate, this is your, again these are your masks, same problem, but now what I'll do is non-conformal. Okay, how will it look like? Look something like this. This is non-conformal. It's not following the so okay, this is, as I told you, evaporation, sputtering are what are known as physical vapor deposition. They are line of sight. This means the metal species are coming from over here. So non-conformal, or what we call is the poor step coverage. Okay, and again in the other case also, the metal was coming from some source, some crucible which I am evaporating or sputtering, using sputtering. Okay, so it just so happens that sputtering is a mechanism which gives good step coverage, or it's conformal. So if you want this to be continuous, then you should use a sputtering equipment. You should use a sputtering technique. If you want like this, there are some applications where we want this, some applications where we want this, depends on the application. If you want non-conformal, use evaporator. Okay, so I should say this is sputter, right? And the one which is below, and the one which is below in the purple one, that is your evaporator. This one is evaporation or evaporator system. Okay, next we want to make 3 microns gate. Okay, this is actually a realistic problem. In a lab we have 3 micron gates. Which instrument should we use to get faster and maximum throughput? Okay, 3 micron gates I can make through all of these techniques: e-beam lithography, steam UV, and optical lithography. All of them will give 3 micron gates. Okay, but we want faster. E-beam lithography writes line by line. It writes like when you want to write a paper. When you are writing on your copy, you write first line, second line, third line, first line, second line, third line, fourth line, and so on. This is e-beam lithography. When you want to make a Xerox of a friend's notes, that's your optical lithography. All of this will happen at the same time, so this is much faster, right? And for this we need 365 nanometer. This is called I line. This is the frequency of light that we use for 3 microns. This is sufficient, 365 nanometers, because the finer, if you want to write finer features, right, I told you 40 nanometers, which my senior did, right, there we used e-beam lithography, because this optical lithography will not give reliable results below 1 micron features. For them we use electron-beam lithography. For here we use optical lithography, because it will reliably give 3 micron gates and faster also, right, and it's a repeatable process. Right, so another thing is now etching. We have called about deposition. Now let's, what do we mean by etching? Again, I'll draw the same. So we have this area is protected by mask, and I want to etch this silicon dioxide. So this is your mask. I want to etch. So if I want to expose it to chemicals, again this is similar that we talked in doping. So the chemicals will come here, whatever the etchant is, and they don't care. They'll etch in this direction, this direction, this direction, this direction, this direction. Right, what you get is you get a profile again like this, an isotropic etch. This is in wet etching. Whatever chemicals you are putting, right, in this case it might most likely hydrofluoric acid, sorry, it will behave something like this. On the other hand, for dry etching, what we use is essentially we use plasma, just like in the ion implantation we did. So here this highly directional plasma is coming. Plasma will strike here also. It will chip away some of it, but this is thick enough. Mask will make sure that it's thick, so it doesn't create any problems for us. So what we do have there then is this highly directional plasma that is coming, right? In the masked region, some of this mask will get damaged, but that's fine, we'll live with that. But we select such a plasma, such a species that will etch away the silicon dioxide, and it will etch only, there will be some small on the sides, but it will primarily you will get this kind of a profile. This is the etched away. And again, as you can see, this is plasma. Okay, this is a physical etching is also happening in some chemical, because it contains some, let's say, fluorine ions which can etch away silicon dioxide. So it will happen like this. Okay, and whatever the byproducts are, they are simply evacuated, because this is happening in a vacuum chamber. So if you want isotropic etching, you go for wet etch. Right. So for the last problem for today, and this course rather, so what does sub-nanometer technology represent in silicon? Sorry, what does sub-nanometer technology node represent in silicon technology? Okay, so I'll connect this with some recent news you may have heard. Tata Electronics is opening a fabrication plant of for semiconductors in Gujarat. That was announced, I guess, a month or two ago, if I'm not mistaken, right? So what the idea is that in the press release, if you say, they'll say, okay, they're investing this many thousands crore rupees, and it will cater to semiconductor needs of India, etc., etc. The technical term that they had used was, it will use this node, 28 nanometer node. I'm forgetting, but I think it's 28 nanometer. Okay, 28 nanometer node. What does it mean? We know nanometer is a distance, right? This means you must be measuring distance between 2 points. Okay. The problem is that now this earlier is it was 28 nanometers, 14 nanometers, 7 nanometers, and so on. You're reducing it, and this is essentially, Moore's law is essentially driving this, because what Moore said, that the number of transistors will double, so per unit transistor cost is reducing. So we shrink these transistors over and over again. Thus we reach this 28 nanometer, 7 nanometer. You will see ridiculous numbers as 2 nanometers, 3 nanometers. So what is happening? So now this distance that we are measuring, so there are various distances that we can measure. So this diagram suggests that. So what is this? Let's focus on diagram B first. Okay, this is source, this is drain, and this is gate, and there will be somewhere over here there will be a gate metal. I'm not this is not shown in this problem. This gate metal. Gate length is one of the most important parameters, as I told you, right? For gate length will determine for RF transistors especially. Gate length is important. Okay. There are other things that you can measure. For instance, the distance between two metal lines. This is called the metal pitch. Okay. There's something else called the poly pitch. So this poly is essentially polysilicon. Think of it as a metallic material. For all practical purposes, think of it as a metallic material. It has properties of metals, and it's used for interconnects. And the distance between two such lines is called what is called as poly pitch. What does it mean? This is a 2D. This is a top view that you are seeing. If I draw a picture of how it looks like, these transistors or these circuits that you see are highly complex. They're multi-tier structure. So on this bottom level, it looks where this is your source, this is your drain, this is your gate contact, right? What happens is that we make these pillars, right? And let's say there is one more device in the same source, drain and gate. What you want is these two devices should have the same gate voltages, right? So what you do is you route it in 3D. This is on the front view that you're seeing. You route this in such a fashion that there's a highly complex, there's a whole fields of designing the layout, right? You want to connect, let's say, source to source. It will be difficult to show here, but you want to connect this to this. Okay. Also, you want to connect drain to drain, and finally you want to connect gate to gate. Now you can clearly see the way I have drawn this is ridiculous. All the lines are crossing each other, they'll short. That doesn't happen. They increase the height of these structures, and then they cross it, take it out on the other behind your screens, right? And then they make interconnects. So these are the interconnects that I'm talking about here. I do not have a good diagram here, but these are the interconnects. These are the metal lines that they are in this semiconductor device, or rather circuit, in this sub-circuit. Okay. The distance between these is the poly pitch, and usually when we talk about nodes, it can refer to both ideally. I mean, that depends on whom you're talking to. So I'll not say, that's highly subjective, but so it can be both A and B, I believe. For some people say it's a channel length, some people say no, it's strictly the poly pitch that is determined. So I leave it open. I'm not confident to answer it one way or the other. Okay. So that ends our session for today, just on time. Tomorrow will be another, the final session, that will be only for 1 hour. And in the last session I received a request that I should do it on MOSFET revision. So I'll try to, we'll again see MOSFETs